and thank you for joining our talk, hAFL1, our journey of fuzzing Hyper-V and discovering a zero day. We'll start by introducing ourselves.
Hi, my name is Peleg Hadar. I'm a senior security researcher at SafeBridge, a cybersecurity company which provides a breach and attack simulation product which helps customers to validate their own security controls. My main focus is on Windows internals, vulnerability research, and hypervisors. And I also gave a talk last year on Black Hat USA and DEF CON.
My name is Ophir Harpaz. I'm a senior security researcher at Guardicore Labs, the research arm of Guardicore, which is a segmentation company disrupting the legacy firewall market. I'm excited by anything low level and also the author of Begin.re, a free online tutorial for beginners in reverse engineering. So why Hyper-V in the first place? In the recent years, many businesses and companies have moved major parts of their workloads to public clouds. And one of these clouds is Microsoft Azure. Now, the virtualization technology the underlying technology for Microsoft Azure is Hyper-V. And we all know that vulnerabilities in cloud infrastructure have massive critical impacts on our information security. So we decided to focus on targeting Hyper-V. And a couple of things we need to know before we dig into this talk, some 101 on Hyper-V itself. There are two types of partitions running on top of a Hyper-V host. The first is the root partition, where the main operating system runs, the host's operating system. And the child partition is where any guest operating system runs, any virtual machine. And there can be multiple child partitions. Now, to provide the child partitions with hardware services, Hyper-V implements para-virtualized devices that consists of a pair for each hardware device. The VSP is the virtualized service provider, which runs on the root partition, and the consumer, or the VSC, runs in the child partition. They both communicate over VMBus, which is an inter-partition communication channel. And whenever it needs to, the VSP communicates with the hardware itself through the VMM, the virtual machine monitor. In our research, the target was vmswitch, which is the VSP virtualized service provider responsible for networking in Hyper-V. Another question to ask is why fuzzing? So we decided that fuzzing would be ideal for us because once we have a good, efficient fuzzer, this will be scalable, and we can find, hopefully, more than one bug. And also, our target vmswitch is quite a huge binary, and we figured that reading its code would be quite a tedious task. So we went for fuzzing. And now some basic concepts in fuzzing. What does a fuzzing infrastructure consist of? The core component of a fuzzing infrastructure is the harness. The harness is the core component responsible for sending fuzzing inputs to the target software. And there are a couple of more components that make a fuzzer actually great in terms of efficiency and performance. The first one is coverage guidance. This means that for every fuzzing input we send to the target, we receive feedback on which lines of code exactly were covered, and therefore we can drive a more efficient mutation process and fuzzing process overall. The second component is crash monitoring, which means that for each crash, we do not only receive the payload that caused the crash, but also details such as the stack trace, the name of the function which crashed, the exact line of code, etc. And the third feature is structure awareness. This means that we don't send arbitrary sequences of bytes to our target, but rather form structured inputs. These can be certain file formats for several targets, or in our case, structured packets. We will see this in the next slides. So first thing first, we need a harness. We need to be able to communicate with our target, vmswitch. The first resource we stumbled upon as part of our open source intelligence was a blog post called Fuzzing Para-Virtualized Devices in Hyper-V. Now, this looked quite good for us because this is what we wanted to do exactly. We wanted to fuzz a para-virtualized device, which is vmswitch. And we actually kind of liked the methodology that was presented in this blog post. The researchers targeted the virtual PCI bus in Hyper-V and not vmswitch. But what they did was to obtain the VMBus channel that the VSC, the consumer, uses on the child partition, and then use this VMBus channel to send inputs to the provider, to the VSP. Once they had this primitive or this ability, they built a fuzzer on top of that and were able to send countless of fuzzing inputs and find vulnerabilities. So again, we decided to adopt this methodology for our own target, vmswitch. And as you can probably imagine, the main challenge here is to be able to actually understand where the VMBus channel is. And this was quite a long sub-project for us. It took a couple of weeks, I think, to find it out, but we sum it up in the slide that you see on the screen. We found that as part of the initialization process of NetVSC, which is the consumer for networking services, it creates a structure called miniport adapter context. Now, just another thing that's worth mentioning is that NetVSC is a miniport driver, which means it communicates directly with a network interface card over Ndis. So it creates this miniport adapter context, and inside this context at offset 18 in hex, it stores the VMBus channel. So this took some time, but eventually we understood that, and we were able to start writing our harness driver. And in order to do that, we first needed to find the ndis.sys module in the kernel of the child partition. So we iterated on all loaded modules and found Ndis. Inside Ndis, we used a global variable called Ndis miniport list, which points to the list of network adapters. We went through this list until we found the adapter that we wanted to fuzz with. And we did this by comparing the names. And then, as you can probably guess, we took the context from the adapter and obtained the VMBus channel from offset 18 in this context. Now, the nice thing is once you have a VMBus channel at hand, you can simply use it with known documented APIs, allocate a packet, and send it over to the other side to vmswitch in our case. So just to get a glimpse of our code, this was the harness driver and a very initial version of it, but we'll walk through it quickly. So here in this for loop, we iterate over all miniport adapters. Once we find the one we need, we fetch the context, and then from the context, we take out the channel pointer. So what we had at this phase was our own driver loaded in the child partition kernel, able to obtain the VMBus channel and send inputs. And we actually managed to send some arbitrary bytes and see them in vmswitch side. But our next challenge was to design such inputs that actually propagate through vmswitch code. So the next step was to look at vmswitch and how it processes packets. Now, as it appears, every VSP, virtualized service provider, every VSP needs to implement a callback called VMB channel process packet. And this callback accepts 5 parameters: the VMBus channel, the packet, some buffer and its length, and some flags. And as you can see here on the slide, vmswitch registers its own callback function called KMCL process packet. This is actually the first function that a packet meets in the VSP side, the earliest point in time. So like I mentioned before, vmswitch does not process any sequence of bytes. It expects actually very structured data that is called NVSP packets. And these packets have many subtypes. Some of them are responsible for initializing the communication. Some of them are responsible for setting the ring buffers that are required for communication, send and receive buffers. I think I forgot to mention them before, but these are ring buffers that are used to transfer data. And one single type of NVSP is rNdis packets. rNdis is another protocol that's responsible for communication between a host and a network adapter. So now that we kind of know the different types of NVSP, we can take a deeper look into the packet processing callback and see the different code flows that originate from it. The first one, as you can see, is the flow that handles initialization packets. The other flow handles Ndis messages, and the third flow is responsible for any other type. Now, we decided to focus on Ndis because of two reasons. The first is that Ndis actually has a lot of logic implemented in vmswitch, so it's just a single type, but it's responsible for quite a lot of code in the driver's binary. And the second is that many past vulnerabilities that we read about were found in the Ndis area. So we simply thought it would be a good idea to start there. Now, the function that you see here, handle Ndis send message, is not a documented function. So we needed to reverse engineer it a little bit. And we found that it receives 4 different parameters. 3 of them were actually passed directly from the parent function, the process packet function. And these parameters are the channel pointer, the buffer, and the packet itself. But there's also another parameter here that is a pointer to an MDL. So we thought to ourselves, what is exactly the difference between the buffer and the MDL? Where does the packet actually lie? We found that the buffer is responsible for some metadata on the packet. It specifies what NVSP packet type is being sent, what is the channel type, whether it is data with 0 value or control channel with the value of 1. And then 2 dwords specify where vmswitch can find the sent data on the send buffer. So it specifies both the index of the section in the send buffer and the section size. So apparently this is one way to send packets through the send buffer. But there appears to be another way to send data to vmswitch, and this is through MDL. And when you send data through an MDL, what you need to do is to allocate some memory, put your packet there, and then create an MDL that points to your new data buffer. And in this case, what the buffer needs to specify is -1 for section index, because the send buffer is not in use at all, and the section size does not matter. We decided to actually take this path because dealing with MDLs was easier for us instead of understanding the mechanisms of the send buffer. So just to kind of sum up what sending packets with MDLs look like, there is the buffer that specifies that an Ndis message is being sent, 1 for control channel, and the important part is the dword that specifies -1 for section index. And then the memory pointed to by the MDL has the actual Ndis packet, both its type and the different Ndis fields that are dependent on the type. So now we were not only able to send inputs from the child partition, we were actually able to design inputs that visit certain functions on vmswitch side. And with this ability, we decided to trigger a past vulnerability with our harness and to test it by that. And we chose this CVE by Lisa SH. We triggered it using our Windows driver, which was the first POC from a Windows guest. And we managed to crash the Hyper-V host. So this was a nice starting point, but this was a good starting point, and now is the time to actually connect this harness to fuzzing infrastructure. And for this section, I invite Peleg and pass the ball to him.
Thank you, Ophir. So obviously, we've completed our first phase of our fuzzing project. We now have our harness, which allows us to send any data we would like to vmswitch, and it is fully parsable. And as Ophir mentioned before, we also have an additional components which we wanted to implement in order to build an end-to-end fuzzing infrastructure. So before we'll dive into the components of the fuzzing infrastructure, let's understand exactly what we expect the setup would look like. And we actually examined multiple fuzzing projects which were open source, and we picked hAFL as it looks very promising and we wanted to use it. So this is how the setup looks like. We have L0, with regards to the L0 and L1 and L2 terms, this is actually described level of virtualization. So L0 is actually the bare metal host, which actually runs Ubuntu Linux with KVM, which is the Linux hypervisor, with kAFL runs above it. We have L1, which is our target hypervisor, Hyper-V, and we have L2, which contains two virtual machines, two partitions. Hyper-V partitions are actually virtual machines. The root partition, which contains the host OS, which runs vmswitch, our target driver, and the guest partition, the child partition, the guest VM, which contains our driver, which sends packets to vmswitch. Now, the thing about this setup is that it actually contains nested virtualization. We have two hypervisors, one within the other, and in order to enable nested virtualization for kAFL, because at this point we actually understood that kAFL does not support nested virtualization, we understood we have some tasks we need to perform. And now let's describe them quickly. We actually have an MSR, which enables the Intel PT technology for the code coverage, which we'll describe later. And we need to enable this MSR for a specific VM. We only want to have code coverage out of the root partition and not from the child partition. We also need to actually read and write memory directly from L0 to L2, as we would like to pass fuzzing inputs from kAFL directly to the child partition. And we also need to handle hypercall directly from L2 within L0. Now, as we worked with pre-allocated time constraints, we actually understood at that point that these tasks might take longer than we allocated, so we decided to find some kind of a workaround. So we decided to not to fuzz from L2 and actually fuzz from L1. And we actually understood that, obviously, once you deploy Hyper-V, you have L0, L1, and L2, vmswitch is loaded to the root partition properly. And once we disabled VTX, which is the Intel virtualization capabilities, obviously Hyper-V won't be able to boot properly, as it doesn't have virtualization capabilities, and it won't be able to boot the hypervisor. So we just use a fallback mode of booting Windows 10 normally without any hypervisor enabled. So we only have L1. But in this particular scenario, we actually discovered that the Windows 10 VM actually contains the vmswitch driver, which is loaded to the system. So we thought to ourselves, why won't we just call handler in this send message function with our fuzzing inputs as a buffer and just send it directly within the same VM? So at this point, we actually understood that as we don't have any working partitions, we don't have any working virtual machines, as Hyper-V is not enabled, we actually don't have VMBus, as no one initialized it before. And we don't have any pointer to a VMBus channel. Now, the first argument to the handler in this send message is a pointer to a VMBus channel. So we had to find one or initialize one. And we started to reverse engineer a lot of undocumented structures and fill it manually. And at a certain point, we discovered the VMS vmnick more function within vmswitch, which is responsible of initializing a lot of the undocumented structures we filled manually and also initializing a VMBus channel. So we tried to call it, and it crashed our system. We analyzed the root cause of the crash, and we discovered that it tries to call a lot of VMBus-related functions. And obviously, as I mentioned before, VMBus is not enabled as we don't have Hyper-V working. So obviously, the system eventually would be crashed. So we actually decided to patch out any call to a VMBus-related logic and VMBus-related functions, because we understood that VMBus is not our target. vmswitch is our target, and VMBus does not interfere with the data that is being sent from the child partition to the root partition. So we were not interested in it, so we decided to patch it out. And in order to patch out or modify any Microsoft signed code within the kernel, obviously you'll have to disable PatchGuard. Otherwise, the system will be crashed. So in order to disable PatchGuard, we have the first method, which is the most common method that we knew at that time, which is attaching a kernel debugger to the OS once it boots. Now, by design, Windows will disable PatchGuard if a kernel debugger was attached during boot time. The thing with this method is actually it might cause a lot of performance overhead because it's waiting for a kernel debugger to be attached. And later on, it will try to communicate with the kernel debugger over the KD protocol. And we didn't want to lose any performance because we wanted our fuzzer infrastructure to be efficient. So we actually found a pretty cool and useful tool called EFI-Guard. EFI-Guard is an open source UEFI bootkit, which enables you to load the Ndis kernel without PatchGuard enabled. And also, it disables the driver signature enforcement mechanism, which enables us to load any driver we would like, including our fuzzer and our harness driver, and pretty easily. So we chose this tool, and it was published on GitHub, and it actually solved our problem. And we patched out the VMBus logic. So now let's take a look at how the setup looked like. So we have L0, our bare metal as before, with KVM and kAFL above it. We have L1, which is this time, it's not Hyper-V, it's a regular Windows 10 VM, because Hyper-V is not enabled without VTX. And we have our harness executable, which communicates with kAFL over KVM hypercalls in order to get fuzzing payloads. Later on, it will send our fuzzing payload to our harness driver, which runs in the kernel, and our fuzzer driver will call handle or send message within vmswitch with the fuzzing payload. And now, obviously, it's working because we patched out VMBus and the system won't crash. Now, we chose to name our fuzzer hAFL1. H is for hypervisor, AFL is for the AFL fuzzer, and L1 as we only use one level of virtualization. We don't have any nested hypervisor. So, as Ophir mentioned before, we've completed the harness part, and we now have the ability to send packets within only a single VM to vmswitch. But we wanted to have an end-to-end fuzzer infrastructure, as we wanted to have more capabilities in order to understand exactly whether our fuzzer is efficient, and we wanted to automate the process as much as we could. So let's start and talk about the first component, which is coverage guidance. And as Ophir mentioned before, coverage guidance actually is being deployed with kAFL. Now, we didn't want to use blind fuzzing, as we didn't want to send a packet again and again, and we wanted to understand exactly whether the packet triggered which code, and understand whether a packet didn't trigger code and we didn't want to use it anymore. So kAFL actually supports coverage guidance out of the box by leveraging the Intel PT mechanism. The Intel PT mechanism, Intel processor trace, actually developed by Intel, and enables one to understand exactly where does the instruction pointer of the CPU was in a certain time and in a certain address space. So it's perfect for code coverage collection during the fuzzing process. And it's important to say, and we will get back to this fact in the next slides, that kAFL coverage guidance works defaultly by filtering the coverage according to the harness process context. What does it exactly mean? It means that we have our harness executable, which sends the payload. We'll understand it in a second. And actually, the code coverage will collect the code coverage mechanism will collect the coverage as long as the context, the current context is our harness executable. If the context will be replaced, it will stop collecting coverage as it wants to understand exactly what code coverage originated by us. So at this point, we actually understood that there is a problem. We have a low basic block count of our code coverage, and it didn't make sense to us as vmswitch contains a lot of code. It's a huge binary, and even a single payload should have triggered a lot of code. And the number was pretty low. And at that point, we actually understood that vmswitch processes incoming packets in a multi-threaded manner. And what does it exactly mean? It means that once we send a packet by calling the handler Ndis send message, the handler Ndis function will push it to a queue, which will be processed, which will process the packet in another thread, which means that the context will be replaced. Let's understand exactly how does it look like in the following diagram. So we have hAFL1 with our harness executable. We have Intel PT enabled because the context is our harness executable, and CR3 obviously assigned to the harness executable one. Now we'll send the packet to the fuzzer driver, to the harness driver, and the driver will actually call the handler Ndis send message. Now, as I mentioned, the handler Ndis send message will actually push the packet to a queue. And once the other thread, the worker thread, will try to process the packet, the context will be switched to the system process. And it actually means that the code coverage will be disabled as the CR3 changed and Intel PT disabled as well. And that's the actual reason we lost coverage. So the solution was pretty simple. We actually disabled the Intel PT CR3 filtering, which means that it will monitor all the executions within the vmswitch address space. And we also knew that as vmswitch was not enabled before, we're the only one who performs operations within vmswitch. Hyper-V is not enabled. So we definitely knew that all of the operations we monitor within the vmswitch address space was originated by us. And this is actually a screenshot of the Lighthouse IDA plugin. And we wrote a script which converts KFL Intel PT trace format to a Lighthouse compatible one. Now it was pretty useful for us because it actually visualized the code coverage for us, and we understood exactly which parts of the code we triggered and which parts we didn't trigger. And obviously we did some modifications to the infrastructure in order to trigger more code. So this was the coverage guidance, and let's talk about crash monitoring. Now, as Ophir mentioned, we actually wanted to have some kind of a centralized mechanism which contains of all of the crashes with a detailed crash, and we didn't want to only know that the crash occurred because we didn't want to reproduce it manually every time we have a crash, because it actually means we need to deploy a VM and we need to reproduce the exact crash, and we need to attach a kernel debugger and understand the exact stack trace. Now, KFL actually is deployed with a very basic functionality of crash monitoring for Windows OS. It actually only signals you that a crash occurred and tells you which payload caused the crash. And we wanted to understand the exact details of each crash automatically. So we actually found a pretty cool implementation of Zen's hypervisor within GitHub. And the code actually registered as a bug check callback, which means that it will be triggered every time a crash occurs. And once it's being triggered, it will actually collect the stack trace of the crash and actually replaces each line of the stack trace with the model name. And in order to send the data from within our driver to KFL, we actually implemented two hypercalls within KVM, which enabled us to send the exact size of the crash dump and then the buffer of the crash dump itself. So this is how it looked like on our fuzzing server. We wrote a script which iterates all of the crashes, tells us which payload caused the crash, and displays the exact stack trace of each crash. We also replaced the function address with the function name. So it was pretty easy for us to understand the exact root cause of each crash pretty easily without leveraging a VM. We just needed to open vmswitch in IDA Pro, and we understood the root cause within 5 minutes. So let's talk about the last component of our fuzzing infrastructure, which is structural awareness. Now, we were handling with a well-specified protocol called Ndis. Now, we knew that it was documented well by Microsoft, and we knew that there are a lot of structures and a lot of messages of Ndis, and we knew that if we would try to mutate fuzzing inputs during runtime randomly, we will probably send dummy packets which won't be parsed because there are a lot of basic checks functionality within vmswitch. So we knew we have to generate packets according to the Ndis specification. So we actually used Google protocol buffers in order to represent the Ndis messages and structures in an easy manner. Now, after we represented it by generating a lot of proto files, we used the libprotobuf mutator library, which is a great library by Google as well, which enables one to use the proto files he generated from some kind of a specification or structures and actually mutate packets of fuzzing or payloads of fuzzing during runtime according to the specification we wrote in the protobuf files. So that actually means that we integrated it into hAFL1 and we were able to generate Ndis packets according to the specification during runtime. And this was actually the last component, and we've completed our whole end-to-end fuzzer infrastructure. We have our harness, we have coverage guidance, crash monitoring, and structural awareness. And that was pretty amazing in that stage.
So what you can see here is actually the user interface of hAFL1. I think 2 hours after it started running on our dedicated servers, I got a phone call from Peleg saying that there was a crash. We started investigating this crash, and we found an actual bug in vmswitch. We started reporting this to MSRC, who assigned it with this CVE. So in the time left, we'll try to understand what the bug is and what are the consequences of it. The call chain starts with control message worker routine, which is the function called once a packet is fetched from the queue that Peleg mentioned before. Later on, it continues to an Ndis handle set message function, which handles set requests in Ndis. Then we have another function. If you see in its name, it handles with IFR, which is an in-flight tracer built on top of WPP software tracing. So we're dealing with some logic related to logging the packet. And eventually, the crash actually occurs in a function that has OID switch NIC request in its name. OID is object identifier, and it simply identifies the type of the set request or query request that are sent as part of the Ndis communication. The next question that comes to mind is, what does this OID do, and what is its purpose? So as it appears, this OID switch NIC request is supposed to encapsulate and forward OID requests from a child partition to a physical network adapter. So actually, it's never meant to be sent from the child partition, but rather from the root partition. So this was actually the first root cause of the bug. vmswitch never actually checked that that type of packet is received from the root partition and not from any guest machine. Now, as you can see in the slide, as part of its structure, the packet has a member called pNdis OID request. This is a pointer to the encapsulated OID request. This is where the original OID from the child partition is. So this actually brings me to the second problem leading to the bug, which is this pointer is never validated. If you're an attacker controlling the kernel of a child partition, you can put any pointer there, vmswitch will not validate it, and this will lead to a crash. So as you can see here in the disassembly of vmswitch, we have the instructions leading to the crash. We'll actually look at the top where we fetch the pointer to the OID request and put it in the register R10. This is quite low level, but this is what actually happens there. And then later on, we dereference this pointer in register R10, and then this leads to the crash. But as you'll see just in a minute, there are harsher consequences to the bug than just crashing the host.
So let's talk about the consequences of the vulnerability. So obviously, we have an arbitrary read vulnerability, which allows us to read any pointer we would like. And eventually, if we'll trigger the vulnerability from within Hyper-V guest, we will crash the Hyper-V host and the whole hypervisor itself. Now, the first question that came in mind was we wanted to understand whether it impacts Azure Cloud or not. And we didn't want to test it out on production. So we just asked MSRC. And MSRC did confirm that the vulnerability did impact Azure as well. Now, the thing that is interesting about this bug is, besides from the fact that it's an arbitrary pointer dereference, MSRC actually assigned it with a CVSS of 9.9, which is pretty high. Now, they actually described that there is a particular scenario which involves a DMA, direct memory access device, which by triggering this vulnerability and reading from the DMA device, you might get more primitives, which might lead to a remote code execution scenario. And that is pretty interesting. Now, we didn't have the time to test it out, but we do encourage you to test it out. And if you have any interesting thoughts or interesting results, please don't hesitate and share it with us on Twitter, and we would like to hear about it more.
So demo time. This is actually on a local environment. We have L0 debugging vmswitch and L2. We were running Packet Sender, which is our exploit program, with the vulnerable OID packet and the size. And once Defender will finish scanning our executable, we'll see that vmswitch crashes on L0 on the debugger. If we analyze the crash, we see the actual pointer that was dereferenced, the invalid pointer. You can see many 4 ones in just a second. There it is. And later on, it says where the module, what is the module that crashed and where. And we're already familiar with this function. So this is a local environment, but as Peleg mentioned, it could impact Azure quite harshly.
So we've actually published our whole project to GitHub. We've published the first part which enabled us to send data from the child partition to the root partition. And we've also published hAFL1, which contains the harness part and also modification of the hAFL fuzzer itself. And we encourage you to test it out and improve it and hopefully find more bugs with it. And if you have any suggestions or thoughts, please open a GitHub issue or send us a DM on Twitter, and we'll try to respond to it.
So thank you once again for joining. If you have any questions, don't hesitate to reach out to us online. Thank you.